Okay, hello everyone. Welcome to our next seminar. So today we have Celia Escamilla Rivera from UNAM in Mexico. So Celia got her PhD from Oxford University and the Basque University in Bilbao before having positions in the ICTP and Nottingham. Before moving to her current position at the National Autonomous University of Mexico. So Celia is a cosmologist, and she's an expert on using cosmology to improve our understanding of gravity. So thank you very much for being with us. And I do, before we begin, I do have to apologize because I massively screwed up with this invitation, and I told Celia the wrong day. So I've given her about 30 minutes preparation time for this seminar, but I'm sure it's going to be great. And so I just have to apologize first of all. But thank you again, Celia, and take it away.
Yeah, thank you very much. No worries. I mean, it's a pleasure always to talk about my current research. So I hope you enjoy a little bit about what I'm going to discuss today. That is basically my current research project that is developing precision cosmology, basically in extended theories of gravity. And the direction that I want to pursue this subject is because I want to understand what is happening with the current one of the current problems in cosmology. This is basically this kind of tension in the Hubble parameter. So when I talk about precision cosmology is because if you think about this, is like instead of using data to constrain the cosmological parameters inherent in these theories, when we talk about precision cosmology, more than the qualitative and statistics endeavor, is about a deeper understanding in the physics behind or even hidden in this theory. So, and this is a pragmatic way to motivate this talk, in the sense that we want to go towards the inverse cosmology problem. That is to say, we want to know if the data can give us information about the nature of gravity. So that is what I'm going to do in this seminar, essentially in 3 sections. First, to give an overview of the state of the art of this unmentioned Hubble tension, H0 tension, specifically behind 2 measurements in the extremes of something called the distance cosmic ladder. And this is going to motivate us to analyze from a Bayesian point of view extended theories that I also call it, these theories are teleparallel gravity, in where basically the covariant action is written in terms of an arbitrary function of the torsion scalar, or consider something called it as a boundary term. But for this stage, I will introduce how precision cosmology can be implemented, specifically in some projects that I have working out in something, a scenario that is called F of TB gravity. And later on, I will detail a couple of advanced numerical methods already employed to constrain these gravity models, and which can possibly be adapted for all extended theories at hand to the ambience known as machine learning techniques. And finally, I will mention some ongoing projects along these ideas. Okay, so let us start with the first target, that is the Hubble tension, the state of the art. So, so far, the concordance lambda CDM model has been incredibly successfully at describing cosmological observations at high and low redshift. Yet, as uncertainties on cosmological parameters keep shrinking using the current data available, a number of weaknesses have emerged, and some of them are related precisely with the dark sector of the universe, and other to the tension problems in H0 and sigma H values. And as an extension, these issues has led us to ask for new physics in at least 3 windows. One in the inflation era, second about the cosmic structure formation, and third, the related with the acceleration observed. But let us focus in the tension problems for now. So in regards to the first problem, so far there are 2 routes to determine the value of the Hubble of the H0 parameter. And first, this value can be measured locally through some methods called the distance ladder method. where for sufficient nearby supernovae type 1a host galaxies, where individual stars can be resolved with the Hubble Space Telescope, the distance can be determined through measurements of surface variable stars, or maybe using this kind of object called the tip of the red Ryan branch. So in what consists this distance ladder method? Well, first, we need to think about this. In the first step, the position of the nearby surface in the Milky Way, for example, is calculated based on the triangulation using more of a telescope. This is a very simple step, and we have a lot of precision in this first ladder. But what will happen if we go beyond to the second ladder? So the second step, the position of the surface in a nearby galaxy is determined based on the calculation of the first front and calibrate against the apparent brightness of a close supernova. So in here, we have like a little error in comparison to the first step. And the things get worse when we go even beyond, when we go to the third step, or a more higher ladder in this case. So what will happen in here is that if we want to know the position of a supernovae in a distant galaxy, well, we need to determine it based on the second tier calculations. So basically what we have in here is like the errors of the second ladder is going to transfer to the third ladder and so on. So maybe this method can develop a systematic error in each measurement. So this can have very high repercussions when we want to extract, or at least to derive the value of each node. Okay, so for example, in this qualitative image of the distance ladder, each vertical segment represents a run, as indicated at the very first stop. So distance to the objects in the upper part are calibrated by means of the lower indicator, and a fiducial screening status of each run is shown under the distance axis. So basically, a run is labeled as a screening when that is the case for at least one indicator. So that is why we can compute very easily between these methods the distance from here to the supernovae type 1a, for example. So when we use this kind of method, the value has been improved at least from 10% to less than 2% along these years. So the value that for each node that we can extract using this distance ladder is around 74.03. So also, this is not only the unique method, at least using this distance ladder, but also we can use a second method and predict the value of each node using the sun horizon observed from the CMB. And the second value obtained from this, using this data, at least at this higher redshift, and extrapolate until today. So based, of course, on the physics of the universe, and this value is assumed to be for a flat lambda CDM model. So although the two values from opposite ends of the universe agrees between 10%. So basically the error bars you can see don't overlap, as we can see in this plot, where is added also the standard size measurements that are given in green color. These standard size are related with the measurements from the gravitational waves. So as you can see, there is a discrepancy around 4.4 sigma between the supernovae data, and even greater significance exceeding the 6%, even when other universe techniques are combined. So moreover, this disagreement does not appear to be a consequence of systematic errors as related with this distance ladder method, but maybe we need to perform reanalysis of data that can show us minimal difference, and as more data and independent methods are using, this discrepancy appears to be is increasing. So this significant tension between both measurements could arise from, for example, for relativistic particles. One scenario is this called the dark radiation. Also, we can consider from non-zero curvature, for example, and also if you want to analyze scenarios related with the early dark energy, increasing their energy, or maybe we require a new fundamental physics to explain this H-node tension. But there has been as well novel measurements of H-node apart from these extremes of the universe. To mention three, we have using a quasar as well that are strongly gravitational lensed. This is, for example, for the Holy Cow collaboration with a value of 73.3 for H-node. That is very consistent with the local distance ladder. And also, we have this value given by the MegaMaster cosmology project that basically has used geometric distance measurements to MegaMaster hosting galaxies, and they derive an independent value for H-node that is given by 73.9 in this scale. So as an extension to the aforementioned techniques, a couple of years ago, was released a measurement of H-nodes using another kind of supernovae, this kind of type 2, that which unlike type 1, these are characterized by strong hydrogen features, and besides using a different calibrator. So this is important because one of possibility is to use this type of supernovae as a standardizable candles to measure H-node. So some advantages are that they are more abundant than the type 1a, and there has a better understanding of the progenitors and environments. So as we can see in this plot, the red fillet region corresponds to the value obtained in this proposal, which is very reasonable, covers the so far H-node measurements from other sources that are reported in here. So at this point, one could imagine that maybe a type 2 supernovae may play an important role in revealing the origin of the Hubble tension. Okay, so the third technique in that regards are the standard sirens. So standard sirens related precisely with from merger events detected through gravitational waves, and are data that are very promising, but the current precision is not sufficient to put strong constraints, and there is only one single electromagnetic gravitational wave counterpart detection so far. So the question when we analyze these standard sirens is how, at comparison to the supernovae type 1a and this distance ladder method, how we can infer a H-node from gravitational waves. So in this graph, what I do is illustrate the statistical relationship between the data and the parameters from the gravitational waves. So the blue circles indicate the parameters that require a prior, and the red circles describe the data measurement, which is conditioning on the analysis. So here we are assuming that we have a measurement of the gravitational wave. For example, this X GW is the set of the detectors. There is a recession velocity that is given in some redshift, and there is also a peculiar velocity in the galaxy neighborhood. So the arrows flowing towards a node indicates that the conditional probability density for this node depends on the source of the parameters. For example, the condition distribution for the observer gravitational wave data that is given by these equations depends on the distance and the inclination of the sources and an additional parameters that I marginalized here. So basically, we can extract precisely a value of H-node if we follow this conditional posterior. So what do we get if we follow this process? So basically, in the plot of the left, we have marginalized the posterior density for the H-node values using a sample that includes a binary black holes and their electromagnetic counterpart. So along with the 1 and 2 sigma constraints given also by the Planck measurement that is given by this pink region, and the shoes that is given by in this green region, the maximum value is around 70 that is given by the standard sirens using binary black holes. And the maximum and the confidence intervals at 1 and 2 sigma for this assure are indicated by these dashed lines. So as we can see, a value for each node extracted by using gravitational waves are in the same region between the Planck measurements and the issues that are related with the measurements for the late universe. So in another figure in the graph of the left, we have the inference about the H node and the inclination precisely of this detector. And the posterior densities of H node and also for the cosinus of this L from the gravitational wave electromagnetic conjoint analysis are given by this blue contour and at 1 and 2 sigma precisely. And also we can draw in the same plot the Planck measurements that is given in green, and also the Schur measurements that are given by Schur in this orange rectangle. So basically the angles of inclination close to 118 degrees, that is equivalent for the cosinus of L equal to -1, indicate that the orbital angular momentum is anti-parallel with the direction from the source for the detector. So this is one technique, and also we can apply this from different objects for this LIGO-Virgo collaboration. And so far, this is all the values that we can extract for H node, for the whole parameter. And one of the most interesting, because as you can see, most of them are more inconsistent with the measurements given by the distance ladder, but others appears to be very close to the Planck or to the early time universe. But basically, the last one is related to the function of a compact 2.6 solar masses object with a 23 solar masses object. So this is the value that we obtain, and this is so far the most well understood, in the case that this value is in the middle between the Planck value and also given by the distance ladder value. But okay, what more we can say about the standard science epoch that we are living now? So basically, the gravitational wave astronomy was born in September 2015. It's just 6 years. In 6 years, had offered us at least 50 graviton waves. That is called in the RON 03A sample. But we hope at least for the next year, because now LIGO is stopped, but we hope that for the next year, we'll have the full O3 catalog already finished. And this catalog is going to contain fusions of 2 binary black holes and also compact objects with 36 and 24 solar masses and all another lower masses. Okay, so as I mentioned it, several methods has been applied in order to determine the value for H node. But as I say, H node discrepancy might be a hint of physics beyond the canonical lambda CDM model. And the most economic possibilities in this direction involve of these that I have listed in this slide. As an example, we can notice if we consider a constant value of the equation of state, if you want to model something like a dark energy things, in this normalized posteriors distribution of H node for different choices of dark energy equation of state is fixed to non-standard values. We see that there is some tension related between them depending on the value of this equation of state. But basically, some values can lie in the region where precisely this H node can be derived from the local distance ladder measurements. The other thing is that more than consider these kind of theories or this kind of models, a few weeks ago was released a review, including a discussion of recent Hubble constant estimates, and also was included a summary of the proposed theoretical solutions. So some of these models are presented in this review, and are formally successfully in improving the fit of the data in the light of their additional degrees of freedom, and also restoring the agreement between the 1 and 2 sigma between the early and late measurements. At least of this kind of a large list of theories, and there are two theories that I'm going to mention almost at the middle of this seminar that I have been working out. We are going to discuss for sure further, are listed here as a possible candidates to alleviate precisely these H-node tensions. Okay, so let's go to the second part, that is basically what will I mean when I call this extended theories of gravity, or how we can escape from these canonical lambda CDL scenarios. Okay, so the possible solutions for the tension for H-node. So a question that has been around for several years is like, could corrections or extension of Einstein's gravity can explain our universe that is accelerating, or could they either give meaning to the bizarre value of the cosmological constant that we observe, or could they replace this cosmological constant by something that looks and acts like a lambda, at least over the range of times and scales of our observational data. So if we want to build a modified gravity theory, that is that's a very useful theorem, and this is what I call the Lovelock Theorem, and it's as follows. The second order local gravitational field equations that you can derive from an action that is built only from the four-dimensional metric of space-time are those of the Einstein field equations with a possible lambda term. So if you want to build a gravity theory that is not GR, we have to break one of these clauses implicit in the statement of this theorem. And essentially, we have 5 options in here. So starting with the familiar Hilbert action for GR. So the first option is, okay, so let us give us of the part that says that gravitational action is built from the metric tensor. So what that means is that we can start adding new field contents, as we can see in here, an example of a simple scalar field tensor theory. Now, the second option is, okay, let us give you of the part that says 4-dimension. So if you want to motivate that from, for example, string theory or these models related with the brains, this call it DGP Models, in here I am just showing some modifications taking this 4-dimensional down, and this is called like a Gauss-Bonnet theorem in this modification. Our third option is more like a mathematical parallel trick that is related with a higher order theory, which means that a theory whose field equations contains greater than second order time derivatives. So like in here, we have a 4th order theory, and usually in this kind of scenarios appear 6 theories, and one of the healthy cases inside of these high order theories are the F of R theories. The 4th option is giving up of the part of the local statement. So we can have this inverse down version and a non-local operator as the inverse of the Klein-Gordon term, like that maybe could explain the current late acceleration without invoking the necessity of any dark energy. And the last thing about this theorem, let us give up of the part that says derivative from an action. And maybe possible the gravity is a special case subject to the kind of modified action principle. So one special proposal in this direction is presented in this work. So basically, as very close relationship between, for example, Einstein and Maxwell equation has not the necessity of an action to derive the field equation. So why not consider that maybe gravity can be derived without having this description about to have an action at hand. Okay, so with these 5 options, we can draw an architecture of all modified gravities that has been appeared in the recent years. So this is an updated version, by the way, and allow me to show you which of them has been constrained by gravitational waves, for example, are indicated in this color, or even pass or not the PPN test. And also, if some of them are viable after the detection of the binary neutron star merged with a speed of the gravitational wave equal or different from c. So this is basically how we classify all these theories that are already available in the literature and also have passed or not the observational constraints also from current and early observations. Okay, so that is how we modify how we can propose a modified theory. But going beyond this formulation, and this is the direction that I want to take to extract precisely the models that can alleviate the Hubble tension, is that first think in GR. So where Einstein puts together this theory of gravity with the tools that he had available at that time. So which was an agreement geometry, which was the Levi-Civita connection, which give a curvature with no torsion, and satisfies the metricity verifying. So we are energy momentum tensor that gives you like the source of the gravity, a source of the curvature, and that curvature for us is the geometry taking a parallel transport of a vector. But later on, Einstein worked a little bit in something called teleparallel gravity. In fact, he wanted to bring electromagnetism by changing the connection from the Levi-Civita, which for most of us will be something related with the Christoffel symbols, to a connection that is also the so-called Weissenberg connection. So where there is not curvature and you only got torsion in this scenario. So like in this plot, for example, at the bottom, which is like a sort of like we are trying to close this parallelogram. So instead of a parallel transport, we have a picture of us trying to close this figure in a certain sense with these two vectors. So at the end, what Einstein was designing was precisely a teleparallel equivalent of GR, which is dynamically and classically for GR for all intents and purposes. So what that means? So how we can think rethink the curvature in one sense. So setting this idea by the famous quote by Wheeler, space-time tells matter how to move and matter tells space how to curve. In teleparallel, we change just slightly the second piece where how to curve, but only if we assume the Levi-Civita connection, and therefore we can change the curvature with this torsion if we assume a Weissenberg connection. So that means that the deformation we get from gravity, wherever it curves or torsion, is a property of this connection. So that is how we can fabricate a new kind of theory that is related solely by these torsion terms. So it's very similar if you want to see from the f of r point of view, but in this case, we have a more naturally and even equivalent theory in related to GR. So some examples along these kind of theories that depend solely of this connection, of the Weissenberg connection, of this torsion, is these models that have this Corsion-Turbaton relationship. But also, this torsion needs to be have a boundary condition. So this boundary condition will be given by this B theorem. So theories that are basically complete in the ambience of teleparallel or a teleparallel equivalent of gravity will be theories that consider this torsion theorem and this boundary theorem. And these theories are the so-called F of TB models of gravity. So if you want to see this from a generalizing point of view, you can consider this action as well. And you can see all the contributions derived or given by this teleparallel equivalent gravity will be in some way directly in this part that usually are related also with the curvature in the standard ways. So far, what we can do with these theories as well, and in comparison to f of r, you have some degeneracy in the sense that you need to consider different models related with this of ft or f of tb. Okay, So some models that are very used in the literature are related precisely with the form that you have in the first part of this table. So very popular are, for example, models that are related with a linear power law-like. Another models are related, for example, with mixed power-like. Another models are related with logarithm terms, and even you can propose a Taylor series and see what happens with higher order terms related with torsion of this boundary theorem. The thing that motivates this is that if you consider all these models, all these already have a good motivations, and some are related. For example, all of them give a stability if you want to design a dynamical system using this kind of family. And also they have also proposed some solutions for the fine-tuning problems, and are most used precisely to describe something in substitution of the dark energy. So basically, all these models can give you cosmic acceleration. The maturity of all of these family of models in teleparallel gravity is that all of them reproduces very well lambda CDM. So this is basically, if you want to understand better the latent observations. And also some of them reproduces a equation of state, dynamical equation of state from these standard models. Which kind of observations has been proved using these, has been tested these models? Well, they are already proved with supernovae, with BAO, and also with cosmic clocks or with the Hubble flow. But we have a very, well, not so bigger, but a quite a vacuum precisely in the yearly universe. So this is the next step that I want to take in this research, to see if these models, if these teleparallel gravity models can work pretty well in the scenarios from early time universe. Okay, so what has been done in related with the H-node tension? So there has been a work that I was developing with a colleague that I presented in this slide, that basically we present a F of TB theory in where you can derive an equation of state, an effective equation of state. And as you can see very easily, if you switch off the part related with the teleparallel or with these boundary and torsion terms, you recover very easily the standard model, the lambda CDM model for this equation of state. But when you turn on these teleparallel equivalent deviations, well, you will see very funny things. And the funny thing is that if you consider a model that is given by this form, for the F of TB gravity, the tension for the H-node parameter is around 67.7 of value. So this is very close to the given by the yearly universe. So we suspect that this theory can alleviate this tension in comparison to the distance ladder method that offers us a higher value for the H-node parameter. And this is using precisely latent observations. That is a funny thing. We are computing the value of H-node using supernovae, cosmic clocks, and BAO. BAO calibrated with late time observations, and the value is very more closer to the early value given by Planck, that closer to this distance ladder method. So this can alleviate precisely the tension with the yearly universe. And the second thing about this theory is also you can extract dynamical solutions of critical points and where you can analyze a very interesting cosmology in there. So this is the line that we wanted to follow with this work. So in this second paper, we study a solution that is basically in the H-node tension problem playground. So far, the proposed autonomous system has been restricted over a constant dynamical variable, and this constraint gives us an equation of state that also we can recover very easily the standard lambda CDM model, but also have critical points related precisely with the values given by the free parameters given by the teleparallel theory of gravity. And also you can obtain attractor solutions and some stable points. But the interesting thing is that you also can extract different values for each node, depending on how much you want to increase this dynamical system. And the thing that we can obtain in here is that, for example, if you want to given some freedom in all the free parameters inside the theory, you can obtain a value of each node that is given by 68.47 of this value. But of course, the error is horrible in the sense that if you want to have all the free parameters in this theory, a higher error you are going to have. But if you take some considerations, for example, over a DOS solution, you will see that the errors goes down and the value of each node also remains around 69, 77. This is quite high, but there is another options that are quite very in agreement with the early time derivation of the H node. And also, well, if you want to consider not only scenarios when you have DOS, but also you have non-zero radiation terms, you will see higher values for the H node parameter. So in some way, with these teleparallel gravity models, you can recover or at least have a direction of which kind of values you can get for each node and relax precisely this tension that is given us by the value obtained from Planck or from early observations. Okay, so this is basically what you can do if you want to explore a little bit at hand, in the sense that here we are only constraining the data, but remember that we want to do a precision cosmology in this direction. We want to use a maximum the data and then see what happened with theory, in this case, if the extended theories or even modified gravity is correct in some way. So now there is a wealth of cosmological observation of exquisite precision. For example, at the same time, new models are being proposed every day. So this is usually done within a Bayesian probability framework. So the question of interest in these scenarios is what are the posterior probability distributions for this parameter of interest given the data I have analyzed. So this is basically solving the cosmology inverse problem. So in practice, all of them has been or are now testing with this list of codes that I put in this slide. But allow me to show you two strong efforts to test our theories at hand. So one of these codes is that I presented here is called Cobaya. This is a code for Bayesian analysis of hierarchy physical models, which general purpose is a Bayesian analysis code aimed at a collection of models. So for example, it can be implemented versions of Ordensky theories of gravity, and why not? We can implement also teleparallel versions as well. And also it has complex interval interdependencies and allows to perform some simulations for astrophysical objects that maybe can also be implemented in regards to, for example, black hole shadows or even gravitational waves. But what has been done using this code? So with the power of these computational techniques, there has been a lot of advances in regards to models of teleparallel gravity that includes only the torsion terms and also the f of Tb. But for example, here I indicate the observables used in this analysis, and I'm going to show at least 3-4 samples. For the green ones, is the one that uses to reproduce this kind of plots, and the red ones are not yet implemented for this kind of theories. So in this case, it was investigated the evolution of the scalar perturbation in f of Tb teleparallel gravity and its effects in the cosmic microwave background anisotropy. So we noticed that there is a small deviation for f of Tb gravity models from the lambda CDL cosmology that is very slightly favored. Lambda CDL cosmology is given by this great contour. So we noticed that the f of Tb models does not show any tension with the Hubble constant, and that prevails in the lambda CDM model. So another case And this is using more data, as you can see. It has considered at f of tb teleparallel cosmological models as a power law-like, for example, and it is possible to find upper limits looking at the very early time behavior. This is satisfying for sure the Big Bang nucleosynthesis data on primordial abundance of helium, for example, in this. So as you can see, again, models that are related with teleparallel gravity using an exponential like, you will see that there has any tension with the late time observations. But other models, as I mentioned, can have tensions in comparison to one specific one. The other example that we can have is, for example, consider another kind of observations. And this is, for example, if you want to use supernovae, BAO, and also cosmic clocks in here. So going further in this work, I provided an insightful test via examples of these, not only f of tb, but also f of r theories or f of r gravities, that can relax the tension using current late time surveys. So it was present a description of both theories to compare between them, and then with their corresponding constraints and priors to study the nature precisely of the equation of the effective equation of state in both cases. And also we can extract cosmic late time acceleration if you want to recover the standard equation of state for that energy. Okay, so what will happen if we use the whole data? So let us suppose that we can recover supernovae, BAO, cosmic clocks, and also the Planck data. So this is a serious analysis in the sense that we are including a measurement that is a kind of can have some bias related with the standard model as it is Planck. But for teleparallel gravity, it has been shown also that when we include some models related with the power law models, has less tension in comparison with Planck data. So Planck data is given by this purple region, and the late data that is related with the distance ladder measurements is given by this yellow region. So as you can see, appears that the models related with teleparallel gravity has less tension with the early data, as I show you in the other slides when I use a dynamical system. So in here we are using now observations, and we are obtaining the same results as well. Okay, so going towards not only constraining the theory with the data, remember that we want to use at maximum this data and see if we can recover a gravitational or at least a gravity theory. So as a consequence of this huge quantity of data, processes derived from a technique known as machine learning is already an ongoing work. So the main idea is from observed or training a serial of neurons, the neurons can be seen as a mathematical approximation of a biological neuron that takes a vector of inputs established by the physics we know. We can perform on them and then finally obtain outputs that in our case corresponds to the very well-known cosmological parameters. And once this is done, it is possible to derive the theory which better represents this kind of data. And the advantage of this machine learning is precisely that it has been used in astronomy for object detection classification, and also we have a cleaning image. We can make schedules depending of the experiments or the phenomena that is occurring in the universe, and also we can make simulations go faster. So far, since recent years, the papers that has been released related with machine learning techniques in cosmology has been increasing in these last months. Apart from using this technique of machine learning by describing or by classifying galaxies, type of galaxy, we can also extract the value of the cosmological parameters. How can we do this? Well, I am showing you only in this part the codes that are almost given in Google that also have the maximum power for using this machine learning. But basically, what happens in cosmology? What happens in cosmology is that, okay, let us using extract the most possible data from an image. In this case, imagine that you have the CMB spectra, and then you train this data by neurons, by sectors, in this case by using a deep neural network. And then after training this data, after your code understands very well how you can reproduce, for example, the temperature power spectrum, well, you can extract also the cosmological parameters. And if you get the value for these cosmological parameters, basically you are having at hand an example, or at least a gravity theory that possible can be derived from this data. So the process that I showed you so far is that, okay, we have the theory and then we use the data to have constraints. So now we are going in the other way around. We have the data and then we are going to see which kind of theory is in better agreement with the data that we are training using these machine learning settings. So this is a project that I developed here in Mexico with my group here that I call Cosmonac. So in Cosmonac, what we can do? So imagine that you are giving me supernovae data. So I am going to train a neuron, or at least a set of neurons to train this supernovae data. And the training that you can see is given by this machine learning at higher redshift. So far, the red points are the observable points given by the supernovae that is only goes to around 2.3, but also you can train even not only to 2.3, but also going beyond, almost to redshift very near to 4. And then if you are training this data with using this machine learning, or a subset of machine learning called deep learning, also you can distinguish between models. So in the second plot that you are seeing in here is like, okay, up to the observational data, lambda CDM works pretty well, but when you go beyond of this training data, possibly lambda CDM is not well, and we require a modified theory of gravity, or a modified model. So in here, we assume a family of modification of gravity. For example, in here we have an exotic fluid called the Chaplain gas. And if you can see, the Chaplain gas is more in agreement with this training of the supernovae data at high redshift in comparison to lambda CDM. So that is how you can make the comparison with this training data in order to extract the better theory, in this case, a modified theory related with this kind of exotic fluid. Not only you can do the supernovae, but also you can employ data from gravitational waves and also from gamma ray bursts. So second work was in that direction. What will happen if I use data from high redshift, and also you can extract very well a technique in which you can train the data and extract the better model. And extract the better model, I mean, I can calculate the cosmology parameters, or in this case, you can do also cosmography parameters, and see which kind of cosmography are in agreement with this training data. And even more, you can use data also from the Hubble flow, in this case from cosmic chronometer parameters. And as you can see in here, the contours are very well done. It's not like in teleparallel gravity that we notice some kind of a lack of convergence, but in here is more convergence using this machine learning training data. And also we can recover a standard lambda CDM model. For example, in here you have trainings for different data, and you cannot see even the deviations between the models is almost exactly the same. So we are reproducing machine learning trainings and comparing with the observed data, and there is not a difference. So we are in a good shape in that way. But another interesting thing about this kind of techniques is that you can reproduce also a method called the confusion matrices. And the confusion matrices is a way to quantify how much the data wants your model. For example, in here, there is a method where they employ a modification of the mass of the neutrino using the CMB data. So in this kind of matrices, you can notice that if you don't have any noise on the data, if you don't want to add some errors in the data, they are very clean, you will see that the data prefers the lambda CDM model, at least 98% if you want to put this in percent units. And you can see that the other models, if you change a little bit the mass of the neutrinos, you will see that also this data apparently wants a 90% or a 72%, or even another model with zero mass neutrinos, you will have a 83%. But what will happen if you add noise to this data? So if you want to add noise to this data, you will see that the data starts to not want anymore lambda CDM. So the other models starts to gain more agreement with the data. For example, in here, a model that is modified with a zero neutrino mass, you will see that now it has a 76% of confidence that the data wants that model in comparison to lambda CDM. And so on. If you want to add more noise, you will see that the models, the modified models in relation with the neutrino mass starts to gain more playground in comparison to lambda CDM. So basically also these deep learning or machine learning techniques can show you how much the data wants a preferred gravity model. But if we can do this for the standard models, exotic fluids, and also if you want to change the neutrino mass, you can do also these techniques for teleparallel gravity. So this classification, as I show in this confusion matrix, you can notice that using a supernovae, BAO, gamma ray bursts, and cosmic clocks training with these deep learning techniques, you will see that of the whole family that I show you in this table, that there is this power law, exponential power law, hybrid, and so on, you will see that the model that is preferred with the combo of this whole data is a model that is called the Linder model in FT. So this is the preference, at least 100% of the data that wants this kind of F of TB models. Okay, so some ongoing projects, just to finish some ideas along these topics that I have talking in the seminar, is that all these techniques are already being employed in not only FOTV, but also in theories as Ordensky TG cosmographic models, and including not only the observations that I mentioned, but also we are include multi-messenger observations, not deriving also from the standard science. Another interesting feature about the extended theories of gravity using precision cosmology is to using not only current but also forecast of gravitational wave training with deep learning, of course. And a third ongoing project that is going to start with a couple of my students is training a neural network with teleparallel gravity to understand the early universe. So this is going in the direction to shed some light in the on the cosmological perturbations. So hope we can find something interesting that can give you at least a model independent way to show the early universe at this level. Okay, so thanks for your kind attention, and your questions are welcome.
Great, thank you very much for that really interesting seminar. Do we have some questions? So I know the people in the room, I think you attempted to ask a question halfway through, but it wasn't very clear. Okay.
Yeah,
go on.
Yes, thank you for a very nice talk. I just wanted some clarification, because I'm not an expert in teleparallel gravity, not familiar much with this. So it's a curvature-free gravity. So you mentioned that it's equivalent of the usual GR. To what extent it's equivalent? So, for example, the precision tests and so on, the usual ones are going through. So I would have thought, for example, that if you have a torsion, non-zero torsion, that somehow induces perhaps also spin-dependent forces or something like that. Are there constraints from there? Or? So
not yet. Yes, sorry?
The precision test, the usual GR precision test, go through with the teleparallel gravity?
You mean in the case of non-zero torsion, you mean?
That's right. Yeah, that's what I would understand, right?
Yeah. Yes. In this case, with not zero torsion, it could be quite difficult to set a constraints because that is very related to the boundary theorem. So if you want to, in this case, for example, let me come back. I think it's very clearly from the Einstein-Cleaver action in this point. So with non-zero torsion, what you will have is basically a dependence fully of the boundary theorem. So it's not it's kind of impossible to have constriction at this level. You need contribution also of the torsion. I mean, you can have a constraining. You can constrain the theory using f of tb without the boundary theorem. But if you switch off the torsion, the problem is that the theory is not how can I say cannot fulfill the Weissenbach connection at this level. So that is the problem. So you will not see a cosmology. You cannot derive directly a cosmology that can be constructed. For example, if you use a theory that uses only a boundary theorem, I mean, you turn off the torsion, you will see that your Freeman equations cannot have a scale factor terms. So if you don't have a scale factor terms, that is not possible. You can find constraints at this level. So I don't know if that is the direction of your question.
Yes, exactly. I was asking generically how viable those torsion non-free curvature-free gravity fields. Yeah, thanks.
You're welcome.
Does anyone else have any questions they want to just shout out? If not, I would just, yeah, I actually kind of had a similar question to Archil, but in a sort of more generic sense. I mean, you talk about incorporating, all sorts of cosmological tests that you can to try and constrain, these extended theories of gravity. Does it make sense, or is it just far too complicated to incorporate these sort of precision tests, so sort of like solar system tests of GR? Is that something that could be done, or is it just sort of maybe not relevant or too challenging?
Well, it should be done. I mean, the easiest part, if you want to compare with f of r, is that in f of t, you can have an equivalent GR. So it's like, for example, in here, if you take the equivalent teleparallel gravity, you are basically playing in the GR field. So in some ways, like this theory passed the solar system test. Why? Because it's an equivalent of GR. That is not the same with the f of r theories. The f of r theories are more complicated because you need to impose something that is related with the rich scale factor, and then check that is a rich scale factor is past the solar system test or not. So at level of TG, equivalent TG is very easily the solar system test, because this equivalent part with the GR. Now, if you want to go beyond far further from the solar system test, that is where the things get messy, in the sense that you are dealing now with torsion and boundary, and not only that, also the torsion and the boundary depends on free parameters that is going to be constraining with the late time observations, and that is going to depend as well of which kind of model. For example, just in this model, it is very easily because you have two parameters. But for example, if you want to consider a Taylor series, you will have a degeneracy of free parameters. And if you want to stop this degeneracy, you need to use more data in order to have at least a confident region in which you can say, okay, this is a very well constrained TG gravity. So that is the messy issues related with TG. That the problem is that you have a degeneracy also related with the torsion and the boundary and the powers or constant that you want to join with this model. But I mean, in some way, this kind of model are very natural in the sense that it's like you are playing in a different field that is similar to GR, but now all is related with this torsion and boundary. And the other thing is that phenomena like dark energy, when you don't need to add a cosmological constant in here, this cosmic acceleration, this work is done by the torsion itself. You don't need to invoke any cosmological constant. So it's like you are erasing this problem of fine tuning and so on. So that is the advantage in some way. And you also can mention, okay, yes, there is another gravity models that F of R that also doesn't need to invoke cosmological constant. The problem is that F of R suffers from Ostrogradski or phantom solutions, and TG not doesn't have this kind of problems, at least at this level.
Yeah, so another very general question from a sort of point of naivety that I have is sort of this issue of the phantom dark energy. So when you have this equation state less than -1, what do you know what the sort of observational and also theoretical status of this sort of phantom dark energy solutions are? I mean, are they sort of seen as something to stay away from, or is there some kind of theoretical reason why you might have a phantom solution?
Yes, well, so far, well, there was a reconstruction of 10 kind of samples. I remember there was it was a nature paper that they reconstructed. They used data, late-time data, using supernovae, BAO calibrated with the supernovae, and also cosmic clocks and another combo of data. I don't remember, but there was 10 surveys in this analysis. So they using these 10 surveys reconstructed the equation of state, and they got it an equation of state, and dark energy equation of state, because it's late time observations that oscillated. So that was very interesting, because this oscillation has never been obtained from observations. At the end, you have lambda CDM, and you want to see this constant, this -1. But it has not been seen that this observation gives you something that is less than -1, and then up down past lambda CDM, and then converts to up top of -1, and then go on. So the people was looking for at least 4 years of theory, or at least a model that can give you an equation of state that have this kind of dynamical behavior restructure. So the current status about what happened with the phantom light is that it's permitted, at least this region is permitted with late observations, but it's not well established at early times. So if you want to reconstruct, for example, CMB data, you will see that regions where this equation of state that give you -1 is not permitted, is prohibited, even it give you some how can I say, some singularities and solutions for this cosmology. So that is the thing. So apparently with late-time observations, you can phantom things are allowed. I mean, phantom square equation of state are allowed, but in early times it's not possible. So, but also that is another truth that we have to take with some care, is that the only early time observation that we have at hand is Planck CMB. So a CMB can have a bias with lambda CDM. So the problem is that if you want to compare any kind of model with this data for sure, this data is going to prefer lambda CDM because they have some bias in there. So I cannot say that, okay, maybe phantom is not, is prohibited at early times, but well, maybe with that model independent measurement for early times can say me, okay, maybe phantom can be ruled out or not, but I need these model independent observations. So let's see, let's hope that, for example, Lisa can give you shed some light in that kind of observations.
Yeah, that's very interesting. So I think I'll stop recording unless there's anyone who wants to jump in with a final question. I don't think so. So